in previous class, we have already seen the composition of two injective mapping is injective, but the converse is basically not true. So that means if the composition map is injective, then the first map will be injective, but we can't conclude about the second one. So now we'll continue the next important theorem. So composition of the surjective mapping is surjective or not. So here our first theorem is if FA to B, if FA to B and GB to C be both surjective map, be both surjective mapping, then the composition map, then the composite mapping, the composite mapping G composed F, this is basically A to C, is surjective. So that means we are saying here composition of two surjective mapping is surjective. Now we come to the solution, or we can think about the proof of the theorem. So what is the proof of the theorem? So what is exactly given? You have given f is a function from A to B and G is also function from B to C. And both are basically surjective. Both are surjective. F is surjective, G is surjective. And this is the composition map G composed F. This is basically from A to C. That we need to show it is a surjective map. Okay. So that means we will prove that every element in the codomain set C must have a pre-image in the domain set A under the map G composed. So what we will do, we will take Z is an element in C. So let Z belongs to C and this is the arbitrary element. So we have to show that there exists a pre-image of Z under the mapping G composed. Now since G is surjective, G B to C is surjective. So there exists at least one pre-image, of Z in B. Okay, so with respect to Z, since G is surjective, so there is a pre-image. So we are considering the pre-image is say Y. And let Y belongs to B be one such pre-image of Z under the map under G. So what exactly mean? So then what we say, Y belongs to B and G of Y will be Z. So this is basically say 1. Now it is given F is surjective. So that means the element Y has a pre-image with respect to the map. So we are considering the pre-image is X. So that means Fx equals to Y. Now since F is a function from A to B, this map is surjective and Y belongs to B. So there exists an element X belongs to A such that F of X equals to Y. Okay. So here X is basically belongs to A and Fx equals to. Now what we'll prove? Now we'll think about what should be the G composed f of x. According to the definition of composition, we can write it G of fx. What is the value of fx? This is basically y. So that will be G of y by 2. Now here we will see by 1, G of y is basically z. So it is basically z. So thus, what we have seen here, G composed f of x equals to z, where x belongs to A. So thus, z has a preimage x in A. So thus, every element in the codomain set C must have a preimage in the domain set A. Why? Because since Z belongs to C, this element is arbitrary, and that is basically under the map G composed F. So that means G composed F that map from A to C is surjective. So that means what we have proved here, the composition of two surjective map is surjective. Now the question is true or false kind. Is the converse true? No, again the converse is not true. So the question is true or false, and with proper justification. So what is the question? The question is given, if G composed F A to C is surjective, then F A to B and G B to C both are surjective. Okay, and here our answer is, this is basically false. So we need proper justification. So why this statement is false? The composition is surjective. That does not mean individually they are surjective. So as for example, if we take a function f z to z by f of x equals to 2x for all x belongs to z, and we take another function g, this is also z to z by g of x equals to box of x by 2 for all x belongs to z. Okay, so here box function is the greatest integer function which is less than equals to x. Then what we observed? We observed G composed f of x. So that means G of fx. So that means G of 2x, because fx equals to 2x. G of 2x, that means 2x by 2, that box. So it will be x for all x belongs to z. Okay, it will be basically box x. And since x is an integer, so that will be x. So what we have proved? We have proved here G composed f of x equals to x for all x belongs to z. So therefore G composed f z to z is given by, okay, so this is basically the identity mapping, and you know the identity mapping is injective as well as surjective. So what we have proved here, since G composed F is basically identity mapping on Z, and identity mapping is surjective. So G composed F is a surjective mapping. Surjective mapping. Okay, so composition map is surjective, but here you will see F is not a surjective mapping, but F Z to Z is defined by Fx equals to 2x for all x belongs to Z is not a surjective mapping. Why it is not surjective? Since if we take the element 3 belongs to Z, any odd element, odd integer belongs to Z, so in that case from codomain, there does not exist any x belongs to Z in the domain set Z such that f of x equals to 3. That cannot hold. So f is not a surjective map. So that means here the composition map is surjective, but individually the function f here is not surjective. So that means the statement is false. Now we'll give a conclusion or remark. Our remark here, our remark is if G composed F is surjective, that does not necessarily implies F is surjective. And you will see the counter example here. Now we'll come to the next important theorem. The theorem is if F A to B and G B to C be both bijective, then the composite mapping G composed F A to C is bijective. This is theorem number 3. And here we have done, this is basically theorem number 2. In previous class we have done the composition of two injective mapping is basically injective. So now we can say we'll prove this theorem by using the following two steps. Step 1, if A to B and G B to C both are injective, so first we have to prove that G composed F A to C, this is injective, where F A to B and G B to C are both injective map. This is our first step that we have already done. So this is your assignment, you will do it. Next, step 2, we have to prove that G composed F A to C is surjective, where F A to B and G B to C both are surjective. That we will prove. That will be our step 2 that we have already done in theorem 2. So combining these two, that means by step 1 and step 2, we conclude that, we say that G composed F A to C, this is bijective, where F and G both are bijective map. Now, we continue one more problem here. The problem is, let Fz to Z be defined by Fx equals to box X, where X belongs to R, and G is another function Z to Z be defined by G of X equals to X plus half, where X belongs to Z. Then our first question is, find G composed F and F composed G, and verify G composed F is not equals to the identity map on R, and F composed G is also, where F composed G is basically identity map on Z. Identity map on Z. That we need to verify. So now we will solve the problem. First we will calculate G composed F and F composed G. So we come to the solution now, where F Z to Z, this is defined by F of X equals to box X, or floor function of X, where X belongs to R, and G Z to Z is defined by G of X equals to X plus half, where X belongs to Z. Now, so here G is basically from Z to R, and F is basically R to Z. So F R to Z, and G is basically Z to R, set of real number. So now here, this is R, this is Z, again R. This function is basically F, this function is G. So now we need to calculate G composed F, and this will be R to R. So since G composed F R to R is defined, so G composed F of X, according to the definition of composition mapping, we can write G of Fx. So G of Fx means box X, and that will be box X plus half. So that means therefore G composed F R to R is G composed F of X. This is basically floor function of X plus half for all X belongs to R. And now we'll calculate F composed G. So this is basically G function. It is given from Z to R. Next, from R to Z, our function is F. So what will be the composition? F composed G, and that will be Z to Z. So the second part, so if we calculate F composed G of X, that will be F of Gx. What will be the value of Gx? This will be X plus half. So f of x plus half. F(x) will be box x, so this will be box of x plus half, or floor function of x plus half, where x is basically the element of z. So therefore, F compose G Z to Z is defined by F compose G of x equals to x plus half for all x belongs to Z. Okay. Now, what will be the value of x plus half? Since x is an integer, so box of x plus half, this will be x because x belongs to Z. And in that case, box of x plus half, that box will be x. So that means this will be x for all x belongs to Z. Okay. So now what we observed, since G composed f of x, this is basically box x plus half, where x is for all x belongs to real number. So that means this is not equals to x for all x belongs to real number. So that means G composed f R to R, this is not an identity mapping on R. So that is G composed f not equals to identity mapping on R. What is IR? Where the identity mapping on R is defined by I of x equals to x for all x belongs to R. Now we come to the second part. Is F compose G is IZ? So what we have seen, F compose G Z to Z, this is F compose G of x equals to x for all x belongs to Z. So that means we can write this is an identity mapping on Z. Now we will do another important problem in mapping. Question is very, very important. Let A and B be both finite set, of n elements, and a mapping A from A to B, this is injective. Prove that F is bijective. That means if F is a mapping from A to B and both the set contain same number of elements, this is N, the cardinality of the set B is N. If F is injective, then we can conclude F is surjective also. That means F is bijective. So how we will solve or how we will prove this problem? What is given? Given cardinality of A equals to cardinality of B equals to N, and this is a finite number. And it is also given if A to B is injective. Map. So what we have to prove? We have to prove F is a surjective mapping. We have to prove that if A to B is a surjective map, That means it is sufficient to prove, that if A to B is, you have to prove it is a bijective map. So that means it is sufficient to prove it is a surjective map. As if is injective already given, so now we have to prove if is surjective map. Okay. So what we will do, since the cardinality of the set N, and it is a finite cardinality, so we can take A equals to some A1, A2, An, and just all A1, A2 are basically real number, and they are distinct, where Ai not equals to Aj for all I not equals to J, and I comma J both belongs to 1 to up to N, because it is a finite cardinality N and all elements are distinct. Now since F is a mapping from A to B and F is injective, so F A1, F A2 dot dot dot, F An all belongs to B, and all Fi's are distinct element in B. So what will be the set B under the map F? That will be F A1, F A2 dot dot dot, F An, where F of Ai not equals to F of Aj for all I not equals to J, and I comma J belongs to 1 to up to N, because they are distinct. Okay. So now this is your A and this is your B, and F is basically injective mapping. Here all A1, A2 dot 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 An, image of A1 is basically F of A1, image of A2, F of A2, image of An, this is F of An, and this elements is also distinct. Now we have to show here F is surjective. So what we will take? We will take an arbitrary element from B. Say let B belongs to capital B. So then B is equals to some F of Ai for some I belongs to 1 to up to N. So that means every B has a preimage. The element B belongs to capital B has a preimage Ai in capital A. So since B is arbitrary, so every element in the codomain set B must have a preimage in the domain set A, So therefore, why? Because since B belongs to capital B is arbitrary, so therefore if A to B is surjective. Now since F is injective as well as surjective, so if A to B is bijective, Okay. Now you have given an assignment here. You will prove. Give an example. Give an example of a bijective map. Okay, the simple question. Except identity mapping. You have given except identity map. Okay. So here we will give one important example and we need to solve the example. Let S equals to -1, 1 open interval. That means all those real numbers such that -1 less than x less than 1. And f is a function from R to S is defined by f of x equals to 1 by 1 plus mod x for all x belongs to R. Then you have to prove if R to S is a bijective mapping. Is a bijective map. That means it is injective as well as surjective. So this is basically self-in exercise. I hope you will prove it. We have done similar problem in part 3. Thank you so much.